So what should we write down for this first one up here?
Compounds start getting taken apart by the water because it's polar.
Okay. What?
There's a big question, I guess.
You didn't see that first thing that was written up there? Huh. All right. Why is this happening?
Because the hydrogen flowing part of it is got a negative charge and oxygen flowing part split it with positive charge.
Okay. The water has the ability to do that because it's polar. So the polar nature of the water molecule allows it to attack. Since it's got both sides, a positive and negative side, then it can attack both the cation with the oxygen side and the anion with the hydrogen side. One other really important aspect about this is water's tiny, right? As far as the size of a molecule, it's about as small as they get. The only thing you can get smaller is having two atoms connected together. So I've got this really, really tiny molecule that's polar, and so water gets termed the universal solvent, and a lot of that has to do with the fact that it's really small. If you want to cut something with a blade, the tip of the blade needs to be what? Say again? Did you say wet?
Well, I was thinking of those machines they do use for the tiles and stuff like that. I don't know.
That just keeps it from like igniting the metal.
It needs to be tiny, sharp.
It needs to be tiny. The edge of a knife blade or an axe or something like that, it's sharp is a way to say what was really happening to the blade is that the edge of the blade is tiny. It is very, very thin. And that's what's going on with the water molecule. It's a very tiny molecule that can wedge itself in between the ions to break them apart. Okay. All right, so somebody give me a soluble compound.
Ammonium.
That's an ion.
Sodium chloride.
Okay. All right, let's go with this easiest one first. So now we can't use sodium or chloride for the rest of this question. So give me another soluble one. Okay. So now hydrogens and sulfates are out. What do you want to use now?
Potassium bromide.
Potassium bromide. Okay, so those guys are all soluble. Great. How about some stuff that's insoluble? I didn't hear you.
The calcium carbonate.
Okay. Now what?
Mercury 1.
Mercury 1. You can't just say Mercury 1. Mercury 1 is an ion. We're looking for a compound.
Mercury 1 iodine.
Okay, great. Mercury 1 iodide, Hg2I2. That is insoluble for sure. Can I go get a container filled with Mercury 1? Why not? You're correct.
Because you will never find mercury as a single, just the mercury. Oh, the mercury 1. Okay, never mind.
Can I go get a container filled with these things?
Yes. Well, probably, no.
Why not? You're correct.
Because I think you said something like you don't find it out there or something like that.
Don't find what?
The mercury is,
This isn't about the mercury.
oh,
I also cannot go get a container of this, or a container
Because
of
you reacted long
this.
ago.
Nope.
Is it because of-
Or I cannot get a container of that. I cannot get a container of, well, I definitely can't get a container of that. That. Why?
Because they're always gonna be attached to something else because of their charges. Because they really want to be.
When I put that table salt in water, the Na and the Cl separate out from each other, right?
Yeah.
So can I separate the NAs, Na pluses out, and go put them in a container? Or have a container that has water in it that just has NAs in it? How come?
It would explode.
No. It lost its electron already.
It's so small, it's hard to separate.
No. Everything that you have is electrically neutral. Meaning when you pick something up, let's say a container of salt water, what is in that salt water? Say ocean water. NAs that are separated, that are floating around, and CLs that are separated and floating around. But exactly the same number of NAs, what can you say about the CLs? It's exactly the same number. Because when you grab that glass of salt water, does it shock you? It'll never shock you. Because you can't go get a container of ions. You can get a container of things that are positive and negative, and their charges equal out with each other, but I can't just go get a container of plus charges, or go get a container of minus charges. We okay with that? So every time you grab something, it's electrically neutral. So up here when I say I want you to write down 3 ionic compounds, you can't just say mercury 1, because 1, that's not a compound, and 2, you couldn't actually go get yourself some mercury 1 without doing what?
Hitting yourself.
No, it doesn't exist. It's impossible. It's not that you don't want to do it, it's you can't possibly do it.
Without separating it from something else.
There's something else going to be with it. And so Camille said iodine. That's great. All I need is something that's got the opposite charge of it. And so then I can go get it. So if I want to use mercury 1, I got to go get it with something else. I can't get it just by itself. One more insoluble compound? Say again? Louder. Octane is not an ionic compound. There is no metal and there is no polyatomic ion there. It is definitely not soluble, but it's not soluble. But in this table, I was asking for 3 ionic compounds.
You combine stuff that's in the same group if it's a metal and a non-metal, like lead and silicon.
Yeah?
So lead to silicon, I don't know then.
Um,
Silicon. Silicon would be something else, right?
What do we do when which one of those 2 things is going to be positively charged, the silicon or the lead? The lead, because it's a metal, so it gives its electrons away. Silicon is closer to fluorine, so it's got to have a higher electronegativity, so it would take electrons. So what do we do with negatively charged atoms? How do we change the name?
Ide.
A what?
Ide.
Ide. Right?
Silicide.
Yeah.
Lead silicide.
Do you think that thing exists?
No.
It probably does. Is it very common? No, I've never heard "ide" attached to the end of silicon before, but I can't imagine that I couldn't make it. But sure, let's go ahead with that. It would probably be that. No, it wouldn't. It would probably be that. Yeah. The lead would have a +2 charge, as you said, lead 2, and then the silicon would most likely form a -4. All right. So we want to balance these equations, add states, and then circle anything that's ionic. All right, so what do I want to do with balancing this first one? Put a 12 right there. Then what? An 11 in front of the water molecule? And we're done with that, right? How about states?
Solid, the first one,
How come this one's a solid?
isn't it like a sugar?
Yeah, it's most likely a carbohydrate. It's got carbons, hydrogens, and oxygens, and they're in nice ratios that make me think that this thing is a sugar. The carbon, solid, and the water, liquid. Do I circle anything up here? Nope, no circle for the first one. All right, how about the second one? What do you want to do for balancing? If I put a 2 in front of the carbon dioxide, I get 2 carbons. If I put a 3 in front of the water molecule, I've balanced out my hydrogens. And on the right-hand side, I have 7 water molecules. On the left-hand side, I have 3. So if I put a 3 right here, then I'm balanced out. State. Say again? I didn't hear you. It's only 2 carbons long, right? So it's not going to be a solid. Your guess as a gas would probably be pretty good, except a molecule that small only has a certain number of combinations, and so I just know that that's going to be ethanol. What's ethanol? Louder.
Liquid?
Yeah, I mean, what is it though? Alcohol. The alcohol that's in beer or wine or spirits. So ethanol would be a liquid in this case. Gas. I'll just put liquid for the heck of it. Do I circle anything? Bless you. Nope, no ionic compounds there. No metals there, no polyatomic ions, so nothing. All right, so how do I balance this next one? The bariums look okay. The chlorides are not okay. The ammonias are okay. So if I put a 2 right there, I think that's it, isn't it? Yeah, 2 Cls, 2 Cls, 2 ammonias, 2 ammonias. So sometimes when you do these problems and you're trying to balance stuff out, you don't need to balance it down to the atom. If you try to balance out a polyatomic ion, it could be faster for you. So how many ammonium ions do I have on the left? 2. So instead of balancing the hydrogens and the nitrogens individually, go ahead and balance out the ammonia over there. So I throw a 2 in front of the ammonium chloride. That balanced the ammonias. It also balanced the chlorides for me, and I'm finished, instead of you counting down to the individual atoms. At some point, maybe it won't work out for you because it's a complex formula, but if you just, can you see the carbonates in there as well? The polyatomic ion carbonate? There's 1 CO3 on the left-hand side, there's 1 CO3 on the right-hand side. So the polyatomic ions stayed stuck together, so you can count that as like an object. Balancing, done with that. States? Yeah, this one's actually hard. I'm going to say that this one's actually hard because, so you're correct. So first off, these are all ionic compounds. Are we okay with that? So we're going to circle all of them. And then what did we say for states for ionic compounds?
Either aqueous or
Solid. So it's either a salt, looks like a salt, it might be colored, but it looks like a salt, or it's been put into water and it dissolves. So let's say I was trying to take barium chloride, the salt, the container I have in the lab, and the ammonium carbonate, the container I have in the lab, and I'm going to mix the 2 salts together. Are they going to react very well? Are we okay with that? That mixing 2 solids together, that they're not going to react very well? The surfaces of the crystals will react, and that's kind of it. You don't really get any other action going on there. So if I wanted to react barium chloride and ammonium carbonate together to get ammonium chloride and barium carbonate, what would you probably do with your salts? Yeah. We're going to talk about this particular type of reaction either today or on Tuesday. But when you see 2 ionic compounds and they're supposed to react together, the only real way to get them to react is to do what with them? Dissolve them. So will this first one dissolve? Chlorides is on that list of things that are soluble, right? So this guy here would be aqueous. Yeah, I understand that this one is difficult because there's no water shown at all, right? There's no water in this entire reaction, so how do you know that there's supposed to be water? And the way, again, is I can't just take two salts and mix them together. They're just not going to react. So the only way to really get two salts to react is make them aqueous. So this is ammonium carbonate state. Is this going to dissolve? It's going to dissolve when it's wet though, right?
Oh, eight.
Because there's ammonium there. Okay, how about this other side? Do you have a barium rule? Was there a barium rule on that list?
No, there's carbonate.
There was no barium rule, but there was a carbonate rule. And what was the carbonate rule?
Insoluble.
Insoluble. Okay, so that makes this guy here a solid.
It says sulfates are soluble except for calcium and barium.
That's carbonate.
You're talking about this list?
Yep.
Number 7.
I know, I'm talking about carbonate, not sulfate. BaCO3.
Oh, okay.
It's the rule right above that, number 7, that, or whatever one that is, right above the last one. And then this one definitely is soluble, right? I don't know why I just wrote an S. This one's definitely soluble because the ammonium is soluble and the chloride is soluble.
Where are you graduated in? I can't.
AQ, AQ, S, AQ. Somebody might want to do this reaction. If you were looking at water, if the water had barium chloride in it, the barium ions are floating around and the chloride ions are floating around. Barium, when it's aqueous like that, is ridiculously toxic. So if you didn't want barium in the water, how could you get the barium out of the water?
Heat the water.
No, didn't we just do it? Didn't we just take the barium out of the water? Did we see that? I had Ba+2s floating around in the water, and they're incredibly toxic to all living organisms. And I dropped this ammonium carbonate stuff in, and the ammonium let go of the carbonate, and now the carbonate's like, I want it to be insoluble. Is there somebody around here that it can be insoluble with? And like, oh, hey, there's a barium. So now it hits the barium, it turns into a solid. Now can an organism drink that barium +2? No, it's a solid. Even if it went through you, it doesn't matter. It's not going to let go. That barium is stuck to that anion. So this is how you can detoxify water with a salt that's got a bad ion in it, with a salt that's got another thing that will stick to it. So what you would see here is a precipitate, right? We saw that precipitate with the silver nitrate and the sodium chloride before. So I'm going to actually take that barium and it's going to, bang, turn into this pale yellow solid and then just fall to the bottom. And then you could drink the top of the water. You could, instead of, it's called decanting, you could just dump the water off and leave the solid at the bottom. But what you did is you took that barium out, which will kill you if you try to drink it. All right, next one. Balancing. The aluminums look okay. I can't use the hydroxides to go to both sides because there's no hydroxides on the right-hand side. The sodium, there's actually only one of those. Looks like I've got 4 hydrogens. 4 hydrogens on the left, on the right or left side. So if I put a 2 right here, my hydrogens are balanced. Oh, is that really it? 4 hydrogens on the left, 4 hydrogens on the right, 4 oxygens on the left, 4 oxygens on the right, 1 sodium, 1 aluminum. Oh, that one was really easy. Okay. States. Aluminum hydroxide. Even if it's wet, it's still a solid. So this is going to be a wet solution. So this guy here is definitely going to be a solid because there's no other option. But if this is wet, it's going to be aqueous, right? So basically what I had is ammonium hydroxide and I dumped some Drano on it because that's what sodium hydroxide is. And then it reacted to give me this sodium aluminite and water molecule. And so is this guy here going to be soluble? There's a sodium there.
You still have,
There's a sodium there.
so everything in group A is soluble.
Right. So this guy here is going to be aqueous. So I know that list of polyatomic ions to you seemed extensive. Does anybody remember me telling you that it was tiny? there is a polyatomic ion from a list that I didn't give you. The list is very, very extensive for polyatomic ions. So does it matter what that polyatomic ion is to determine what its solubility is in this case? No, it doesn't matter what the sodium is attached to. It's going to let go when it goes into water, so that's going to be soluble. So even if you are unfamiliar with the anion that the sodium or potassium or any of the group 1 metals or ammonia are attached to, it's still going to let go. Okay, looks like iron, if I put a 3 right here, I can balance the ions out. If I put a 2 right here, I can balance the phosphates, PO4 to 2 PO4s. And then I've got a 6 sodiums here and 6 chlorides, 6 chlorides. All right, I'm good with that. So, oh, we got to back up for a sec. That is an ionic compound, that is, and that is. So those first 3 in that last problem need to be circled because they're all ionic compounds. Solubility. So on this left-hand side, I have 2 salts, right? So how do I react them? I get them wet. So if I get iron 2 chloride wet, is that going to dissolve? It's got a chloride on it, so that'll be aqueous. What about the sodium phosphate? For sure, it's got a sodium on it, so that'll be aqueous. And on the other side, I've got iron 2 phosphate and table salt. So yeah, table salt will definitely be soluble. What about that iron 2 phosphate? It is not. There isn't a rule about iron, but there is a rule about phosphates, and the phosphate rule says I'm insoluble. So if something's not superseding that, like on the reactant side, the sodium superseded the phosphate rule, then this guy here is going to be a solid. And then I'm going to circle everybody over here. All right, let's do this last one. Balancing it, what do you want to do? C3, this 1 sulfur, 2 iodides.
Put a 2 in front of the
A 2 here. No, a 2 on the H2O isn't going to work because we have 4 oxygens on the left, right? Correct? And I've only got 1 on the right-hand side. So if I put a 4 right here, so my oxygens are balanced. Now I have too many H's on the right-hand side, correct?
Yeah, but if you put a 2 in front of the I, and then a 4 in front of the HI.
Put a 2 right here.
In front of the I. Yeah.
Put a 2 right here.
Or, I mean, a 2 in front of the HI, and a 2 in front of the I.
A 2 here and a 2 there.
Yeah.
No, because now there's 4 I's on this right-hand side, and there's only 2 I's on the left-hand side. Let's erase this 2 for a sec. So I got my oxygens balanced without this 2. How can I balance out the hydrogens? I put a 4 right here. So that gives me 4 and 2 is 6, and there are 8 and 10. So no, that didn't work. Put a 6 here.
Yep.
So 6 there, a 6 right here, and then 2 more here. That gives me 8. There are 8 right here, but then there are another 2 here. I put an 8 there. So now I've got 10 H's on the left. Are we good with that? And on the right, 10. Okay. Do I need to mess with that H2S, that hydrogen sulfide? I don't. There's only 1 S on each side, and that's good. So the only thing I need to do is drop a 4 right there. Okay. State, this first one. We had the acid discussion, right? It's either a gas or it's aqueous. I'm not going to be messing around with gaseous sulfuric acid, so same situation, aqueous. Same thing here, aqueous. I go over to the other side. What is this thing right here? It is an acid, but I just made this acid, so what state is it?
Gas.
It's a gas. This is one of the stinky compounds from rotten eggs, hydrogen sulfide. I2, what state's that? Periodic table. It's solid. Just look on the table and you see the elements solid. And then it's water. Anybody ionic here? That's an acid. Yeah, you could circle it or not circle it.
Are acids ionic?
They behave a little bit differently, but that's fine. It's got a polyatomic ion, so that's good. And then if we're going with that difference in electronegativity for that one, that's it.